All right, let's do some gas stoichiometry. So gas stoichiometry, as with all stoichiometry, starts with a balanced chemical reaction. However, in gas stoichiometry, we're going to be using the ideal gas law to relate the amount of the substance to the pressure, volume, and temperature. So it's all about the mole. Let's look at problem number 1. 3.25 grams of potassium chlorate decomposes at 610 torr and 34 degrees Celsius. What volume of oxygen gas is produced? First things first, we have a decomposition reaction involving potassium chlorate. So in this case here, potassium chlorate will decompose and it's going to turn into potassium chloride and oxygen gas. So we have our balanced chemical equation, and we've also written down the amount of our starting reactant of potassium chlorate. That's going to help us keep in mind where we're going to go. Because in the end, we're being asked, okay, how much? We're being asked about this gas, and we're not at STP anymore. So we're going to need to use Stoich to find out how many moles of the gas are produced. And I think you see where we're going in this video. We're only going to do 2 practice problems here. Let's write down what we know. Well, we know we're going to use the ideal gas law. We know we're given pressure in torr, so we're going to need to get that into atmospheres. Temperature in degrees Celsius, we're going to need to get that into Kelvin. And of course, the ideal gas law we know. And first things first, let's find moles. Then we can find volume, which is ultimately what this question is asking. Okay, let's convert the torr into atmosphere. There's 760 torr in 1 atmosphere. Therefore, we get 0.803 atmospheres for our pressure in this problem. Next, let's get out the mole map here, and let's see where we're going. Well, we're starting with a mass of a substance here. So we're going to use molar mass. We're going to convert it into the moles of that substance. Then we're going to convert it into moles of substance B, in this case, oxygen gas. And then we're going to use the ideal gas law to solve something about gas B, not at STP. And in this case, we want to know the volume of oxygen gas. So there's how we'll use the mole map in this problem. All right, so let's get at it. We have our grams of potassium chlorate, and from the periodic table, we can find the molar mass to be 122.55 grams in 1 mole. And using stoichiometry and our balanced chemical reaction, we are able to relate these molar ratios to convert ultimately into 0.040 moles of oxygen gas. And again, here is our mole ratio of stoichiometry. Next, ideal gas law. Mathematically, let's rearrange this to solve for the volume and plug in everything we know. And since we've converted grams to moles and atmospheres, we've already done that, and we've changed our temp to Kelvin. This is a plug and chug, and our volume is equal to 1.26 liters of oxygen gas. And what's so cool about this is we're not at STP, and we're using stoichiometry and combining everything we've learned thus far. Let's do one more problem in this video. Copper 2 oxide reacts with carbon to yield carbon dioxide gas and solid copper at 32 degrees Celsius and at 87.3 kilopascals. We're given a volume in milliliters that is collected over water. How many grams of copper 2 oxide reacted? I'm going to go ahead, underline that. Underline this needs to be switched. This has to be converted. This needs to be converted. And we're going from one substance to another substance. So we're using stoichiometry as well. First things first, what do we know? Let's think about what we know. Well, we know stoichiometry always starts with a balanced chemical reaction. So here's copper 2 oxide. When mixed or added with carbon, yields carbon dioxide gas and solid copper. Balanced chemical reaction means we can move on to the next step of this problem. What are we trying to find? Well, we're trying to find how many grams reacted initially. And we're given quantities that will allow us to relate the gas to another substance. Let's put down what we know. Pressure, volume, temperature, moles, ideal gas law constant, all of our gas conversions for pressure, and we are gonna take 32 and add it to 273 Kelvin. So we know we have 305 Kelvin, check. Next, we've bumped our decimal and converted milliliters into liters, acknowledging there are 1,000 milliliters in 1 liter, and that's where this 0.0345 comes from. Next, let's convert our pressure into atmospheres. There's 101.3 kilopascals in 1 atmosphere, and that gives us 0.862 atmospheres. Okay, so we have all those basic conversions done, which means we are now ready to deal with our vapor pressure. In the last video, Gases 6, we talked about vapor pressure extensively. We also talked about Dalton's law of pressure and partial pressures. I gave you some intuition leading up to the fact that, hey, when we collect a gas over water or we bubble a substance through water, we're going to need to account for the fact that there is water vapor that is also exerting a pressure in addition to, in this case, carbon dioxide gas. So you're going to need to get out your table that you should have taped in your composition notebook. You're going to look for 32 degrees Celsius and the corresponding vapor pressure given in millimeters of mercury is 35.6. So remember that number, 35.6 is the partial pressure exerted by water at this temperature. We have our starting pressure. As it was, we converted this from kilopascals into atmospheres, but now we need to subtract the partial pressure, the vapor pressure of water. So 35.6, remember I told you we'd use that. So all I'm doing here is in one step, I am converting millimeters of mercury into atmospheres. We do that by dividing the quantity in millimeters of mercury by the number 760 millimeters of mercury, because that is equal to 1 atmosphere, as you can see at the bottom of your screen. So that's going to give us a new pressure of 0.815 atmospheres. Okay? So we have now accounted for that partial pressure exerted by water vapor. This will give us the pressure of the carbon dioxide gas. Now we can take that number and now we can finally use the ideal gas law. So rearranging this to solve for N, or the number of moles, gives us the following. Because we've solved and we have all of these quantities. So this is a plug and chug. Let's go ahead and get our number of moles here. with three significant figures, 1.12 times 10 to the negative third moles of carbon dioxide gas. But we're not done yet. Now that we have moles of carbon dioxide, we've found moles, so now we need to do a mole to gram stoichiometric calculation. Let's go ahead and do that here. Let's look at our mole map. On our mole map, we're going to be going from, in this case, we found the moles of one substance, and we had to use the ideal gas law. So we use ideal gas law to find moles of A being the carbon dioxide. We're going to use a mole ratio in stoichiometry to convert that to moles of B, which is the copper 2 oxide. And then we're going to use molar mass to find the grams. Pretty cool stuff. All right, let's do some stoichiometry. We have our value that we calculated here. If you're wondering, what's this? That's the moles of the carbon dioxide that we calculated down here using the ideal gas law. Now we know we can use a mole ratio. Okay, so using the mole ratio, we have 1 mole of carbon dioxide, and that relates to 2 moles of the copper 2 oxide. So there's our mole ratio for the stoichiometry. Now we're going to use molar mass. We know in 1 mole of copper 2 oxide, there's 79.55 grams. So we're moving along here in our dimensional analysis, and we can solve to get 0.178 grams of copper 2 oxide. That is how many grams initially reacted to yield a volume of gas at a given temperature, pressure, and volume. In our Georgia Standards of Excellence, we're now combining 2 different standards. We're looking at the moles of a gas, but we're also now looking at stoichiometry and combining all of these ideas together. I'll see you guys in class.